Just as people are joining, so let us wait for a few more minutes, and after that we can start with the session. I guess some more people would be coming, and then we can start. Okay, so I think we can start with the live session. So I welcome you all to the live session of week 1 on the course Fundamentals of Protein Chemistry, which is taken by Professor Shagata Dasgupta of IIT Kharagpur, and I am Srijan Sen from IIT Kharagpur, and today I will be taking your first live session on this particular course. And firstly, I would be discussing in brief. Firstly, I would be discussing in brief the lectures and the lecture which is being taught to you, and then I would be discussing a few questions which would help you in solving the assignment. Okay, so I would be following this procedure for all of my live sessions. So, okay, so I am sharing my slide. So, is my screen visible and am I clearly audible?
Yes, sir.
Okay, that's good. Fine. Okay, so let us start. Okay, so in today's lecture, we would be discussing mostly about the amino acids, then somewhat about a few informations about spectroscopy, and then what are the different types of amino acids, and then the related aspects of this. Okay, so this is the first lecture. It would be a simple one. So most of the informations would be known to you or you have studied in the basic level. So just a brief information. So what is so just amino acids and the structure of amino acids. So the term amino acid might mean any molecule which contains an amino group and any type of an acid group. So however, it is mostly refers to an alpha amino acid and a carboxylic acid. Okay, so the simplest amino acid that is known to us is the amino acetic acid, which is known as the glycine, where this R group is hydrogen, and there are other common amino acids, but the entire symbol for this stands what is shown over here, where we have the amino group. This is our acid group, and in the alpha carbon we have one hydrogen and an R group, and this R group is a variable group, and depending on the R group we can classify these amino acids um, in so we can classify these amino acids in 20 different types. So the simplest amino acid known to us is glycine, and then we see that when R equals to a methyl group, then it is alanine. Okay, so what are amino acids? So the monomer units from which we can form long polypeptide chains of proteins, or the building blocks of proteins, are called these amino acids. So L-alpha amino acids and their derivatives participate in the different cellular functions, such as you can say as its diversity in the nerve transmission and the biosynthesis of porphyrins, purines, urea, pyrimidines, and different nitrogenous bases over here. And the short polymers of amino acids are known as your peptides, and these have different roles in your neuroendocrine system as hormones or neurotransmitters, neuromodulators, hormone releasing factors. So there are hundreds of amino acids which are found in nature, but we are only considering the 20 amino acids that are needed to make all the proteins that form the human body, as well as the different forms of life. And these 20 amino acids are the L isomers of the uh, amino acids. So we only find the L amino acids which is prevalent. The D isoform is not so prevalent in the form of amino acids. There are obviously exceptional cases. So all of them except for glycine contains the chiral alpha carbon, and these amino acids are the L isomers with an R absolute configuration, except for glycine, which does not have a chiral carbon, and cysteine, which has an S configuration because of the sulfur containing R group. So based on this, we are classifying the amino acids and giving a brief information about what amino acids are and which form it is more prevalent. So we can see that humans and other animals cannot synthesize 10 of the L-alpha amino acids present in proteins, and in in high amounts, and to support the infant growth or to maintain an adult health. So there are those are, you can say, the essential amino acids which are needed by the body, but the humans and other animals cannot synthesize these amino acids and have to be provided from outside for the growth and maintaining the health. Now these are the structures of the 20 different amino acids. We have to remember these structures because there would be definitely a few questions from this. And these amino acids are classified on various aspects. So this is the chart key which says that amino acids can be classified based on the side chains, say aliphatic side chains or aromatic side chains, and on the charge on these amino acids. They can be acidic amino acids, basic amino acids, and also on the side chains, whether they have an hydroxyl group or a sulfur containing group or an NH2 group, on what they have, and which amino acids are essential for us and non-essential for us. So this is the entire chart which we have to keep in mind, and probably we have to practice these structures from time to time such that we can keep in mind as to which structure is for which amino acid. So this is an important slide. Okay, so if we see that for an alanine, it has an aliphatic side chain and it contains a CH3 in its R position, as I've shown previously that this is the ultimate or the basic structure of an amino acid, and the variable portion is the R group. So for alanine we have a CH3. Then for glycine, which is not a which does not have a chiral alpha carbon, so there is hydrogen, and then we have the isoleucine followed by leucine, and this the proline ring has an amino group. Then we have valine, which also has an aliphatic side chain and it's an essential amino acid. Then we have the phenylalanine, where we have a phenyl group along with a CH2. Then we have a tryptophan, then followed by tyrosine, where we have a phenyl group the phenol group, and then a CH2 is also attached to its para position. Then we have an aspartic acid, which is an acidic amino acid. The glutamic acid is also an acidic amino acid, and these are non-essential amino acids. Followed by we have arginine, which has an NH2 group in its side chain, and we call it as a basic amino acid. Then we have the histidine and lysine, which also falls in the category of the basic amino acids. Then we have serines, serine which has a SH in its side chain. Threonine has an OH, the serine has a OH group in its side chain. Cysteine has a SH group in its side chain. Threonine has a OH group followed by a CH3, and methionine is also a sulfur containing side chain with a CH3. Then we have asparagine and glutamine, which have amidic side chain. So here we have the glutamic and the aspartic acid, and when the OH is substituted by an NH2, we get the asparagine and glutamine for their respective amino acids. So this is the entire structure of the 20 amino acids which we need to keep in mind. And now we can categorize these amino acids. Now there are polar amino acids, non-polar amino acids, and on the basis of that we can classify them according to their hydrophilicity and hydrophobicity. So 10 amino acids are polar amino acids, which are aspartic acid and glutamic acid, which are acidic amino acids. Then arginine, lysine and histidine, which is basic. Then we have cysteine, asparagine, glutamine, serine and threonine, which are neutral yet are polar amino acids. And the polarity of these amino acids depends on the side chain. You can also see this group where we have classified the 20 amino acids into the hydrophilic group as well as the hydrophobic group. And the polar amino acids tend to make hydrogen bonds with suitable groups using your the hydroxyl group, the OH group, and the NH2 group, the amine group. And the polarity of these amino acids affects the overall structure and the function of the proteins. And like you have the sickle cell anemia, right? Okay, so moving on. These are some of the essential amino acids. So humans can synthesize about half of the amino acids which are needed to make the proteins. The other amino acids are called the essential amino acids, which must be provided in the diet, and these amino acids are not prepared by the body, so we have to provide them from outside through our diet or our food habits. Now the 10 essential amino acids are the following. So among these we have arginine, then valine, methionine, leucine, threonine, phenylalanine, histidine, isoleucine, lysine and the tryptophan. So these are the 10 amino acids which are essential amino acids, and these are not made by the body. So we have to provide these via some kind of diet or the food that we eat on a daily basis. Now proteins that provide us all the amino acids in the right proportions through the nutrition that we take are called complete proteins. And examples of these complete proteins includes what we eat daily, like the meat, fish, milk, eggs, and it is about 50 grams of complete protein per day is necessary for the adult humans. And proteins that are severely deficient in one or more amino acids, so some diet that you take up might not contain a lot of amino acids, so these are called incomplete proteins, and these what is necessary for the function of the body. So these are called incomplete proteins. Now if the protein in a person's diet comes mostly from an incomplete source, then you would see that the amount of human protein that can be synthesized is which is limited by the amounts of the deficient amino acids. So when you are not taking enough proteins in the when you are not getting enough amino acids that will help to provide you that essential protein, or that would be necessary for your body to function, those we call as first of all incomplete proteins, and this can lead to different kinds of diseases, disabilities and all inside your body, and diseases, infections. Okay. Now, coming to the acid base properties of amino acids. So, although we write the amino acids with an intact carboxyl and an amino group, their actual structure is ionic and depends on the pH. So, depending on the pH, because we can see there are a lot of groups that can take up charge, that can take up hydrogen ions and give up hydrogen ions, or are and can involve in different acid base reactions. So based on this, so what will determine that? The pH determines the how much hydronium ions or the H plus ions is present in the solution, or if the hydronium ions is deficient in the solution. So this is going to determine what charge your amino acid or your entire protein is going to take. So if we see that the carboxyl group loses a proton to give a carboxylate ion, whereas the amino group is protonated to an ammonium ion. So this structure is called your dipolar ion. So you can see mostly when the amino acid is near its pi or the isoelectric point, then you can see that these amino acids would love to stay in the zwitterionic or this dipolar form. So here we have the uncharged structure, and so this is the way as we usually write, but we are supposed to write it in this zwitterionic form where the amino group is charged positively charged, and the carboxyl group is a carboxylate ion where it is negatively charged. So the dipolar nature of these amino acids gives us some unusual properties. So what acid-base properties of these amino acids are actually doing? So amino acids have high melting points, generally over 200 degrees centigrade and Celsius, and glycine, which has a melting point of 262 degrees Celsius. And if we see that these amino acids are soluble in water, then they are in any kind of organic solvents like ether or dichloromethane. So not all amino acids are very soluble, because there are obviously hydrophilic amino acids are which are not soluble in water, and they would love to stay inside the core of your protein. So now, as of now, we are seeing from the perspective of an amino acid or the building block of a protein. But if we when we would be studying in the future, when we would be going through the future lectures, we would be seeing that it's all about the proteins that matters to us. So then the orientation of the amino acids would actually matter. So as of now, the amino acids are soluble in water more than in the organic solvents, and these amino acids have much larger dipole moments than any simple amines or the simple acids. So if we see that glycine has a dielectric dipole moment of 14 D, then propylamine is 1.4 D, and your propanoic acid is 1.7 D. So amino acids are less acidic than most of the carboxylic acids, as well as they are less basic than the most amines, because they have both the groups. So they would be somewhat in the center, or neither too acidic than the carboxylic acid, or neither too basic than the normal amines. Okay, so because these amino acids contain both the acidic and the basic groups, they are amphoteric. That is, they have the acidic and the basic properties. Now the predominant form of the amino acid depends on the pH of the solution. In an acidic solution, the groups are protonated to a free group, and the molecule would be having an overall positive charge. And as we raise the pH, or we add amounts, increase the concentration of your hydroxyl ion, the hydroxide ion, then we would be seeing that these protons would be grabbed more easily, and it would be giving us a negative charge to the entire amino acid. So we see that as the pH is raised, it loses the proton, and this is the first dissociation constant, and on raising it further, the group loses proton at about 9 or 10, and this is the second acid dissociation constant, and the molecule gains an overall negative charge. So you will be seeing that as most proteins as more the amino acids which are having your charged group side chains, okay, like NH2 or the carboxyl group. So they would be having more than more than two dissociation constant. So based on that, we have to calculate the isoelectric point of such particular amino acids. Now, what is this isoelectric point? Now, an amino acid bears a positive charge in the acidic solution, and we know that it bears a negative charge in the basic solution. So, there must be an intermediate pH where the amino acid is mostly balanced between these two forms, or it would love to stay in the dipolar ion or the zwitterionic form, and with a net charge where is 0, and this pH is called the isoelectric pH or the isoelectric point. So that point is called the isoelectric point, and the pH in which it maintains that zwitterionic form, or where the charge is 0, is called the isoelectric pH. Now we see that the side chains of aspartic and glutamic acid contains acidic carboxyl groups. Now these amino acids have acidic isoelectric points around pH of 3, and an acidic solution would be needed to prevent the deprotonation of the second carboxylic acid group to keep the amino acid in its neutral isoelectric state. Whereas what we see for the basic amino acids like arginine, then lysine and histidine, that they have isoelectric points at a pH of say higher than 7, like 7.6 for histidine, then for lysine it's 9.7, and for arginine it's 10.8. Now what we can confer from this value is that they are reflecting the weak basicity of the imidazole ring, then the intermediate basicity of an amino acid, which we see for a lysine, and the weak basicity for an imidazole ring is for an histidine, and it's for an intermediate basicity for a lysine, and strong basicity of the guanidine group that is present in arginine. So a basic solution would be needed in each of these cases to prevent the protonation of the basic side chain, to keep the amino acid electrically neutral. Now there are other amino acids which are considered as neutral with no strongly acidic or basic side chains, and their isoelectric points are slightly on the acidic side because the NH3 group is slightly more acidic than the COH group, which is a bit more basic. Right. So now coming to another thing. Now we have talked about the acid-base reaction of these amino acids and the isoelectric points. Now we will be discussing something about buffers and why buffers are important. So we see that biological systems use buffers to maintain the pH. We say buffering range. We say for anything that we are using for biological samples, we do not give biological samples a very high acidic or a basic condition. So we do not give a very high acidic or a basic condition. Rather, we mostly keep these specimens or your biological samples mostly in the buffer conditions, say at between 5 to 8 or 6 to 9, like that, in this buffering range. So what is the definition that we can provide to this term buffer? So a buffer is a solution that resists a significant change in pH upon addition of an acid or a base. So when you're adding very small amount of acid or a base, the pH won't be differing that much. So if we see from the diagram that there is a water of pH 7, and the moment we are adding say HCl, then the pH moves to 4. There is a sudden drop of pH and it becomes an acidic solution. Now we cannot call it a buffer, it's an acidic solution. Whereas when we are giving some amount of say sodium hydroxide, then the pH suddenly moves up above 10.5, and we call this as a basic solution. This cannot be considered as a buffer. What is a buffer that we see from the second image is that it's a pH 7, and then on adding of a small amount of HCl or some amount of your sodium hydroxide, the pH does not vary much. There is a very small shift in the pH. and this is what we call as a buffer. So it is a mixture of a weak acid and its conjugate base. Now, a bicarbonate buffer is a mixture of carbonic acid, which is the weak acid, and the bicarbonate ion, which is the conjugate base. So H2CO3 and HCO3 minus. Now, all the hydroxide or the H plus ions that we are adding to our buffer are consumed, and the overall H plus concentration or the pH does not get altered to that extent. Now if we see here that for carbonic acid and the bicarbonate ion with an H plus gives us 2 moles of carbonic acid, and carbonic acid plus bicarbonate ion plus your hydroxide ion gives us 2 moles of bicarbonate and water, one water molecule. So this is the buffer solution, or this would be equilibrating in this two ions. These two ions would be equilibrating in the buffer solution for a bicarbonate buffer. And for any weak acid by conjugate base pair, the buffering range is its pKa of plus minus 1. Now coming to the Henderson-Hasselbalch's equation. So when we speak of buffers, the first equation that comes to our mind is the Henderson-Hasselbalch's equation. So the dissociation of a weak acid is mathematically described by the Henderson-Hasselbalch's equation. So if we have an acid, say HA, and then it dissociates to give us H plus and A minus, and the equilibrium constant is your Ka. Then how we can frame the equation is like the equilibrium constant or your Ka is equals to your H plus ion concentration into your the conjugate base ion concentration divided by the acid concentration. And when we put all these equations together, when we are putting all these equations together, then we can see that, and after taking log, because after all we have to frame this equation in such a manner such that we can relate the pH with the pKa and the log of the conjugate base, or the you say the acid by the conjugate base. So here we have to frame the equation in such a manner. So we know pH equals to minus log of H plus. So we have to frame the equation in this manner. So as of now it stands as K equals to hydrogen ion concentration into conjugate base ion concentration divided by the acid concentration. And when we take log on both the sides and rearrange them, then what we get is pH equals to pKa plus log conjugate base ion concentration divided by the acid concentration. And here the conjugate base ion is your A minus, so A minus concentration divided by your HA concentration. That will be inside the log, and you have pH related equated with your pKa. Now and here we can see if Cb is the conjugate base and the weak acid is Wa, then pH equals to pKa plus log conjugate base by weak acid. And this entire thing is your Henderson-Hasselbalch's equation. And if your pH is equals to your pKa, that indicates that your acid concentration, or the molecules of your acid concentration, is equals to your conjugate base concentration. So what are the different applications of your Henderson-Hasselbalch's equation, and why do we at all need to understand this Henderson-Hasselbalch's equation? So if we see over here that why do we need to understand the Henderson-Hasselbalch's equation, is that it is needed to calculate the ratio of your conjugate base to your acid if the pH is known to us. For regarding this equation, you can expect a few good questions in your assignments as well as when you're going to give your exams. It's a very important equation, and it actually, so you would be given the pKa, because the pKa value is a standard quantity and the value is known. And if the pH is known to you, or people ask you to calculate and prepare a buffer of say 20 millimolars of pH 7. Say you are preparing an acetic acid buffer, okay, and then you know the pKa value of it, and then they say make a buffer of say 5, and then you can calculate the conjugate base concentration and the weak acid concentration, and then you can measure those ions, and you can take sodium acetate and measure it, and then take that amount of acetic acid and put it in and make prepare that buffer. So it is important to calculate this particular ratio. Now we have to also calculate the pH if these entity is known to us, or this particular ratio is known to us. Then it will also help us to calculate the pH, and also calculating the pH of a weak acid solution of a known concentration using this Henderson-Hasselbalch's equation is also useful. Now we can also determine, for example, we do not know the pKa, although it's a standard quantity, yet let us assume that we do not know the pKa value. Then we can determine the pKa value of this weak acid conjugate base pair. And on changing the pH when strong base is added to a solution of a weak acid, we represent this as the titration curve, and we would be observing a few titration curves of a few amino acids in the future slides. And also, and what we at all mostly need to understand is the pi, or the isoelectric point of this amino acid. So all these applications are so important, uh, and therefore we need to understand this, or therefore the study of this Henderson-Hasselbalch's equation has come up, and it's a very important equation in terms of buffer, and also it would be important for your assignments and the exams. Okay, now moving on to a term called electrophoresis. Now, electrophoresis uses the difference in the isoelectric points. So, electrophoresis, as we can understand, is movement according to the electric charge. So, electrophoresis uses your differences in the isoelectric points of the different amino acids. We know that amino acids, each amino acids have different isoelectric points, and we can separate them based on these isoelectric points by performing electrophoresis. So a streak of amino acid mixture is placed in the center of a layer of acrylamide gel or a piece of filter paper, and then the two electrodes are attached to the two extremes of this particular say matrix, and then a potential of several thousand volts is applied across this electrode. So the voltage can vary, and you are applying a voltage to this particular matrix where you have a mixture of amino acids. So when this matrix has say this agarose gel, or this matrix has your mixture of amino acids, and you give it a voltage, then it would start separating. So the positively charged amino acids would be moving towards your cathode or the negative electrode, and your negatively charged amino acids would be moving towards the positive electrode or the anode. And the amino acids whose isoelectric point has no net charge, it would show any mobility, and it would remain mostly in the center. And now let us study an electrophoresis with the differently charged amino acids. So we know that there are there are negatively charged amino acids as well as positively charged amino acids. So the negatively charged amino acids are called the acidic amino acids, and the positively charged amino acids are called the basic amino acids. So this is what we know. The others are falls in the category of the neutral amino acids. Now, if we see that there is a mixture of alanine, lysine, and aspartic acid over here, and this is the matrix, and it is wet with a pH of 6 and a buffer solution, and you're providing it a power supply, and the voltage is on. Just a small information to whoever is coming. Try to be there by 6:05 or 6:10. Okay, because otherwise it becomes very difficult, because sometimes I might not hear the notification and I might not be able to give you the entry to this meeting. So try to stick to a particular timing. Probably 6:10 would be good, because like that also I study 5 to 10 minutes late. So try to stick to that timing, because it's good to be punctual as well. And now we are providing a power supply to this mixture of amino acids of alanine, lysine, and the aspartic acid. Now what happens? If we see that the buffer solution is of pH 6, we have to keep one thing in mind, that when the pi of an amino acid is less than your pH, then that particular amino acid attains a negative charge. So when your pi is less than the pH, then what happens, that pi has to go up to reach that particular pH, and on going up or to reach that particular pH, it will be negative charged. And therefore we can see that the pi of an aspartic acid is less than the pH that we are providing, that is 6. So aspartic acid would be negatively charged and would move to the positive charge, that is towards the anode. Whereas when the pH is less than your pi, so for lysine the pi is say 9, and then 9 or 9.7, and then we are providing it a buffer or putting it in a buffer of pH 6, then what happens, the pi has to come down or move, has to downgrade to reach the pH of 6, and on downgrading it attains a positive charge. So remember two things: pi less than pH means it will, the amino acid will attain a negative charge, and pH less than pi means the amino acid will attain a positive charge. And that's why we see here that at pH 6, alanine, which is a neutral amino acid, won't be having any charge, and it has a particular pH of I guess 6. And whereas on the other hand, your aspartic acid, which has a pi of 2.8, would be negatively charged, and lysine having a pi of 9.7 would be positively charged, and therefore lysine would be moving towards your cathode and the aspartic acid would be moving towards your anode. And in this particular manner you can separate a mixture of different amino acids. And now there would definitely be a question like, we can separate these amino acids in this manner. What would happen if there are two neutral amino acids, or two basic amino acids, or two acidic amino acids? So they would also be separated based on their pi. So if we see that when we have aspartic acid, which of a pi 2.8, for example, we are taking glutamic acid, that is also an acidic amino acid. So how would we separating them? So in that case, we have to also consider their pi. So what we are seeing over here is the pi, right? So aspartic acid has a pi 2.8, glutamic acid say has a pi of 3.4. So what we would be seeing over here is that your aspartic acid is moving over here, whereas your glutamic acid say would be moving over here. It would be moving slowly because it has a less negative charge. Now for the same is observed when it is for lysine or an arginine. So lysine has 9.7, say arginine has a higher pi, so it would be, say arginine would be moving over here and lysine as it is moving over here. So in this manner we can actually separate the two amino acids even if they are of the same charge, as we are separating them based on their pi. So now we have performed the electrophoresis, and this is what is written over here. Is there is a mixture of alanine, lysine and aspartic acid, and at a pH 6, and your aspartic acid would be negatively charged moving towards the anode. Alanine won't be showing any mobility, and your lysine would be moving towards the cathode. So after a period of time, The separated amino acids would be recovered, the cutting of paper or scraping of the bands. You can scrape off the bands out of the gel, and then you can treat these reagents with ninhydrin to make the bands visible, and then you can identify them by comparing the position of their with the standards. Now you have a standard, and then first of all you treat them with ninhydrin to give them a color, and that would be your Ruhmann's purple color, and then you do it with compare them with a particular standard to find which of these are the particular amino acids. Now coming to the titration curve of glycine. So this is very important because the titration curve or the dissociation constant, the equilibrium constants are so important. And what at what pH would so we are telling PI. So how are we determining this PI? And the second thing is that we have to also understand that at what pH a particular amino acid is fully positive or fully negative, or is it existing in the neutral charge or the zwitterionic form. Now you see that the curve starts at the bottom left where your glycine is entirely in the positive or the cationic form, and at pH. Now there can be a question like at pH 0 what is the charge of the glycine, at pH 2.3 what would be the charge, at pH 6 what would be the charge, at pH 9.6, and at pH 12 or higher. So as we start from the bottom left where glycine is entirely in its positive form or the cationic form, and when we are increasing the concentration of the OH minus, or say we are adding equivalent amounts of sodium hydroxide, then the pH, and we are recording the pH. So as the pH touches 2.3, so half of your glycine would be present in the cationic form, and half of it would be present in the zwitterionic form. So at pH 2.3, the concentration of your cationic glycine and the zwitterionic glycine would be equal. Now as we move up and the pH reaches 6, all the glycine is converted into your zwitterionic form, and on further increasing the OH minus concentration when the pH reaches 9.6, then half of your zwitterionic ions would be converted to the glycinate form or the negative anionic glycine, and in because this carboxyl group would be the hydrogen of this carboxyl group the hydrogen of this amino group would be grabbed, and it would attain a negative charge. So in the first case what we see over here, and at 9.6 it becomes your negatively charged and becomes the basic form. So what happens from the beginning is that in the first case the first charge is on this amino group, and just as the pH is increasing or we are adding OH group or the OH or the hydroxide ion, we are increasing the concentration of the hydroxide ion, then the charge would be, or the hydrogen would be lost from this carboxyl group, and finally the charge would be lost from this amino group. So first the charge is gained by the amino group, and then it is lost from the carboxyl group, the side chain carboxyl group, and lastly the H plus ion is lost from the amino group. So this pattern is what we have to remember. Now we can see that the glycine is mostly in the cationic form at pH below 2.3, and in the zwitterionic form between 2.3 and 9.6, and in anionic form above 9.6. Now by varying the pH of this solution, we can take the control that on what charge this molecule is actually having. Okay, and how we are calculating this PI? So it is the half of the addition or the mean of your pKa1 and pKa2. So pKa1 plus pKa2 divided by 2 is how we are calculating the PI. Now what happens when there is a side chain, or there is when the side chain is containing a charged group or a carboxyl group or an amino group? So what we see over here is the glutamate or the glutamic acid, and here what we are seeing is for arginine. Now, when there is glutamic acid, there would be an additional COH group or a carboxyl group in the side chain, right? So what happens over there at the very low pH or at pH say below 2.19, the glutamate or the glutamic acid would be mostly positively charged, and it is plus one, is in plus one state. Okay, so here we are having the charge of plus 1. Now, as we are increasing the pH, what happens? The charge from the side chain the backbone carboxyl group loses the hydrogen ion, and we are getting a negative charge over here. So the overall charge over here is 0. So this is the zwitterionic form. Now on further increasing the pH, the side chain carboxyl group loses the hydrogen ion, and we get a anionic group or the basic form where the charge is -1. And on further increasing your pH, so this has 3 equivalent points. Here we get the first equivalent point, then we have the second equivalent point, and this is the third equivalent point. Now, when we have increased a lot of the pH, then we get a charge of -2, where we would be having, where the proton would be lost from this amino group. So first glutamate has a charge of +1, then it goes to 0, then -1 and -2. So in this case, the question is, how are we then going to calculate the PI? Because now we do not have 2 pKs, we have 3 pKs. And which 2 pKs are we going to consider? Is it 1, 2 or 1, 3 or 2, 3? What would be that be? Now, for when the side chains have charge groups, then what happens? Which 2 pKis are we supposed to consider? So the 2 pIs which we are supposed to consider is when your amino acid is moving to a zwitterionic form, when your amino acid is moving to a zwitterionic form, and from that zwitterionic form it goes to another charge. So say you have a +1 to 0 and 0 to -1. So the 2 PIs which we are supposed to consider is pK1 and pKr. So these are the 2 PIs which we would be taking and adding these 2 and divided by 2, and we get the ultimate PI. So for this case, the PI would be 2.19 plus 4.25 divided by 2, which comes to about say 3.15 or something, 2.2 and 6.4, and that is coming around 3.2, right? So now for arginine, what happens? So here arginine, has an amino group in its side chain, so that would be also having a positive charge at a very low pH. So here we have so at less than 2 we would be having arginine in the +2 state. Then when we are increasing the pH, say we have increased the pH to 8, then we arginine would be, then the carboxyl group would be losing a hydrogen, and it would be in +1 state. So arginine moves from +2 to +1, then it goes to 0 at pH or the zwitterionic form at pH 10.8, and finally it goes to the basic form or the negative form of -1 in at a pH higher than 13. So arginine has, so what we see here for arginine is that it goes from +2 to +1 to 0 to -1. So the pi or would be calculated on the basis where it is moving from +1 to 0 to -1. So these are the two pKa's that we would be considering. And if we see from here that pK1 is 2.1, then pK2 is 9 and pK3 is 12.5, then we can tell that the pi is somewhat 10.8. It lies between 9 and 12.5. The other way which you can consider is that the two closely related pKa's you can take and divided them by 2. For an for an acidic amino acid, like 2 and 4 are very close to each other, so divided by 2 is 3, and 9 is very far from these two, so you not consider them for calculating the pH. For arginine, 9 and 12.5 is close, so you add them and divide by 2, and 2 is very fast, so you need not consider them. So this is a simple way as to how you can also think, but the basic concept is how I explained you. So as we move from a +1 to 0 and then to -1 and +1 to 0 to -1. So these are the two pKs which you would be taking. Okay. So I would be moving to UV visible spectroscopy and a few aspects of spectroscopy. So, okay, so I would be giving you a 5 minutes of break, and then we can again restart. Okay, I think that would be good. So this, we would start at 7:05. Okay, so let us continue. And okay, just for your information, that these live sessions would be recorded and would be uploaded in the YouTube in my channel. And the NPTEL team would also be sharing with you this particular link for your future references, and I would be also sharing the slides with the team, and you can actually contact them, or I do not know how they share to you. So probably they would be also sharing with you the slides as well as the YouTube video link, for in case you have missed it, or if your friends have want to look into these videos, you can also take them, right? So this is just so these live sessions would be are being recorded, right? Okay, so let's start from the UV visible spectroscopy. So if we see that UV radiation has a wavelength which ranges between 220 to 380 nanometer, and the visible radiation has a wavelength of 380 to 780 nanometers. Now, the substances can absorb varying amounts of UV and visible radiation at different wavelengths, and colored compounds absorb energy in both the UV as well as visible region of the electromagnetic spectrum. Now, these substances can be liquids or solids, and the measurements are made using your spectrophotometers or the spectrometers. So, we measure the wavelength in these particular instruments, and these substances can be your solids or liquids. And nowadays these modern instruments are also coupled with their microscopes to allow them see the solid samples and very small samples of solids and liquids, such that you can also analyze them both qualitatively as well as quantitatively. Now, what is this UV visible spectra? Now, you have an incident light of 254 nanometer, and you have a transmitted light of the same particular wavelength. Now, in the middle of this, you have a particular sample. Now, what happens? This sample would be absorbing something, would be absorbing some light, would be taking up something. So, the intensity of light that you are providing to this sample, and then when you're detecting the transmitted light, the most of the time what you would be observing is that there is a difference between the intensity that you provided, or the incident intensity, and the transmitted intensity. Now, if a particular wavelength of UV or visible radiation can be isolated from that source and passed through a sample which it can absorb some radiation, then the transmitted light intensity is IT, which would be less than the incident intensity light, or I naught. And that the amount of light that would be transmitted with respect to the incident light is what we are calling as transmittance, or T. So transmittance is equals to your transmitted intensity divided by your incident light intensity, and this entire thing is what we are calling as transmittance. And remember, this is a very important formula which you need to remember, because this would be also useful in solving a lot of questions which you would be getting in your assignments. So keep this formula in mind. And now the sample can absorb all or none of the incident light as well. So it can actually absorb the entire light, or it can actually take up no light. So there are also some substances which do that. And when we are calculating this transmittance in terms of percentage, so percentage transmittance equals to your transmitted intensity divided by your incident intensity into 100. Now we have to what we get in. So for example, we are measuring substance in a spectrophotometer. Then what do we get actually? So we do not get the transmittance. We probably get the incident, the transmitted intensity. But the mostly you would be seeing that whenever you are measuring a sample, then you would be getting its absorbance. So if it's a protein, you get an absorbance of at 280. nanometers. If it's a nucleic acid, you get it at 260 nanometers. So you are getting the absorbance. So absorbance is the factor that is mattering to us. So absorbance is the minus logarithmic of your transmittance. So A equals to minus log of your transmitted intensity divided by your incident intensity, and your absorbance can be calculated in this manner. So this equation is very important and you have to keep this in mind. So mostly we in terms of percentage, when we do it, it's like the incident intensity is always 100%, and then on the basis of what we get as the transmitted intensity, we calculate it. So another equation that you can also keep in mind is absorbance is equals to your 2 minus log of your transmitted intensity percentage. So if you have to calculate transmittance in that manner, like there would be an equation that percentage transmittance equals to 50, so 2 minus log of 50. So in that manner you can also calculate the absorbance. Now when we are plotting the absorbance versus your wavelength, we get the absorbance spectrum, and this can be this is a particular absorbance at A, where we are seeing an absorbance at 280 as well as another at say 280, and then for B we are seeing two absorbances. Okay, one at say 240 and another at around 340. So with the advantage that absorbance measurements are usually linear with concentration, absorbance spectra can be used. So this is absorbance versus your wavelength. And now when we throw these equations into the different laws of spectrophotometry, then we can actually get a linear plot where we would be plotting absorbance versus your concentration and your the length of the cell in which you are measuring your sample, and from there you can actually get the molar extinction coefficient. So this is actually said in the laws of spectrophotometry. So there are two basic laws, and the third one is a combination of both, and we what we know in our daily life is the third law. So the first law is your Lambert's law, which says that absorbance is proportional to the path length or the cell in which you are measuring the say the cuvette, or the cell in which you are measuring the biological sample and or any kind of a sample. And the Beer's law compares the absorbance with concentration. So when we actually join these two, absorbance proportional to length and absorbance proportional to concentration, then what we get is absorbance is proportional to concentration and length, and we have to give it's a proportionality. Now we have to give it a proportionality constant, and this proportionality constant is called the molar extinction coefficient. And your absorbance is a ratio, therefore it has no particular unit. So when we calculate absorbance equals to your epsilon CL, and where your epsilon equals to absorbance divided by your um, concentration and the path length, and on putting the different units of concentration in moles per liter and the path length to be in centimeter, we can say that molar extinction coefficient has a unit of mole inverse liter centimeter inverse. And also as we know that 1 liter equals to 1000 centimeter cubic centimeter, so your unit of molar extinction coefficient would be 1000 centimeter square mole inverse. So these are the two units of your molar extinction coefficient, and you can expect an MSQ like this. There you would be given 4 options of the units of molar extinction coefficient, and you would be asked to as to which two of them are correct, or which of these are correct, or the units of molar extinction coefficient. Then you have to take these two answers. So what is the importance of this Lambert-Beer law? So we know that absorbance equals to your epsilon CL, and absorbance is proportional to your concentration, and therefore it should have a linear relationship. So when you plot absorbance versus your concentration, then you are taking a sample and you have different concentrations of that particular sample. You measure the absorbance of this particular sample and you draw a straight line. So this is going to be a straight line, and then what happens, you take unknown solution and also measure its absorbance and say you do not know its particular concentration. So there are, you would also be finding some proteins which cannot give a particular absorbance because of the lack of the the aromatic amino acids, and therefore this you have to calculate in this manner where you are plotting absorbance versus your concentration. Now there is a standard concentration, known samples of different concentrations. You measure the absorbance, and then what you do is of the unknown absorbance that you are measuring, and when you measure it according to the absorbance that you obtain, you can find the actual concentration of this particular unknown sample. So in this way, this law is would be very helpful, and this linear relationship actually helps you in finding the absorbance as well as the concentration, and along with that you know that the slope that you would be getting is would be equal to your epsilon value. So from here also you can calculate the epsilon value, right? Now we have spoken a lot about, now getting once more back to from where we started, the amino acids. Here we have to consider as about the polypeptide chain or peptide bond formation. So how is a peptide bond getting formed? So we know that the amino groups, the amino acids have the amino group as well as the carboxyl group. So via the dehydration reaction or the loss of water, so so from the carboxyl group the OH is lost, and from the amine group the H is lost, and in the form of a dehydration reaction you get a peptide group. So in this manner the peptide bond formation occurs. So you can get a series of peptide bonds, the series of amino acids joined via these peptide bonds. So each of the peptide bond formation is involved via this dehydration reaction or this loss of water. So there is a equation, there is a figure where you can see methionine, we have aspartic acid, leucine, tyrosine, and all are joined via this peptide bonds via the loss of this water. Now what are the characteristic features of this peptide bond? So these are covalent and strong bonds. So the for a protein molecule, or this is the strongest bond that you would be observing for the proteins. So it's a covalent bond, and this has a partial. So what gives this peptide bonds its strength? So that is its partial double bond character. So how has this theory arose? So the distance for a double bond is 1. So the distance of this partial double bond is 1.32 angstrom, which is the middle of the single bond, which is usually 1.49, and a double bond which is usually 1.24. So from here we can tell it's a partial double bond character, neither totally it's a single bond or totally a double bond. And this peptide bond is rigid as well as planar, and the prevailing trans configuration of neighboring alpha carbon groups, and the side chains are free to rotate on either side of the peptide bond. So this is the backbone which is being created. So when we tell about backbone atom, so in the backbone atom we have this carbon, alpha carbon, we have the carboxyl carbon, we have this nitrogen, amino nitrogen, and another carboxyl, another alpha carbon. So these actually alpha carbon, the nitrogen, and the carboxyl carbon actually forms the backbone of your peptide bond. Now there are different types of bonds that occurs in a protein molecule. We have the covalent bonds, which is your peptide bond and the disulfide bond, and also your non-covalent or some weak bonds like your hydrophobic interactions, then your ionic bond and the hydrogen bond. So this is about the peptide bond and how the peptide bond is being formed, and what are the different types of the bonds which can exist in a protein molecule. So as of now this is about the theory part, and then I would be moving to a few problems, and I would be solving a few problems such that it would help you in doing your assignments, and what type of questions can actually you can expect in your exam, that you can obviously guess from the questions which I solve, and as well as what you can see in your assignments. So how I do these problems is like that: I would be showing you the questions, and you are the people who would be answering me, and then I would be discussing with you the questions, the answers of these questions. So you can answer these questions to me in the chat box, such that there is no rush. And so the first question which says is, which of the following sets contain all polar neutral amino acid residues? So which of the following amino acids are polar as well as neutral? So in option A we have glycine, aspartic acid, asparagine, glutamic acid. Then we have in B is phenylalanine, tyrosine, and tryptophan. Then we have serine, cysteine, and threonine. And lastly, we have isoleucine, valine, leucine, and methionine. Anybody trying to answer? You can answer to me in the chat box, because that will actually be helpful. So every one of you should be answering these questions, because these questions are very easy. You do not have to fear whether you are giving the right answer or the wrong answer. It does not matter as of now. Okay. Okay. So C A, how many? So what's the population? So Priya has said A, Samadrita C. Okay, C A C C. Anyone else who wants to answer? Any other answers? So the first question, so the first option that says is, we have to find the polar as well as neutral. So it has to be neutral as well as polar. Now when I say glycine, aspartic acid, asparagine, and you say glutamic acid. Now what happens? So these are acidic groups. These are not neutral groups. Okay, so in that manner, the first option gets deleted. And the next one is, those have your aromatic side chains, and those are hydrophobic groups as well. So some of them are hydrophobic as well, so they are not polar. Now coming to option D, which is isoleucine, valine, leucine, and methionine, these are all hydrophobic in nature, and they are neutral though, but they are hydrophobic and non-polar in nature. So C is the right option. That is your serine, threonine, and cysteine, and this contains your polar neutral amino acids. So the side chain of a serine has an OH, the side chain of a threonine has an OH with a CH3, and your cysteine has an SH. So C is the right option. Okay, moving to the next question. The following sulfur containing amino acids are found in proteins. So which two would you expect to find in proteins? And these are sulfur containing groups. C, B, C, C, B. So people are confused between B and C. So one is cysteine and cysteine. Achha, any one of you can tell me what are the differences between these two? What is the difference between these two, cysteine and cysteine? So the question that it says is the following sulfur containing amino acids found in proteins, yes, has a single cysteine residue and cysteine is a dimer. Right. So cysteine is a monomer. It has a single cysteine residue, whereas that has a is involved in a disulfide bridge. Correct. So if we see over here that sulfur containing amino acids which are found in proteins. So in proteins, it is not that we do not find the dimer, but the most relevant answer over here would be your C, because methionine has a S. Okay, so it has a sulfur containing amino acid, and this cysteine, the cysteine, which is in your dimer form, it is involved in a disulfide linkage. So the main amino acid is your the cysteine, that is your monomer, but the dimer is involved in the disulfide linkage. So that's a disulfide linkage and not a amino acid. That's an amino. The two amino acid, the cysteines are involved. That's true, but over here the right answer would be your methionine, which already has a sulfur group in your side chain, and the other one would be your monomer form of your cysteine. That is the cysteine one. Okay, and those who have given answer D and D, its selenocysteine does not have a, okay, so you say C, but selenocysteine does not have a sulfur group, it has a selenium group in place of your sulfur. Anyways, that's not a problem, so just saying that. Okay, question number 3. An amino acid with a neutral side chain has pK1 of 3.4 and pK2 of 9.4. What will, at what pH would this amino acid migrate towards the anode? Okay, so possibly there is a technical glitch, so I'm not being able to connect at present, so I am discussing the questions and answers over here. So if we see that the pH, the amino acid with a neutral side chain has a pK of 3.4 and the pK2 of 9.4. So at which value of pH will the amino acid migrate towards the anode? So when we calculate the pi as pK1 plus pK2. So if we see that when we take the pK1 of 3.4 and the pK2 of 9.4 and divide by 2, we get a pi which is equals to your 6.4. Okay, so the pi equals to your 6.4. So now the pH, at which pH will the amino acid migrate towards the anode? So for it, the pH, so as I was saying, only when the pH is above your pi, then only it will be negatively charged and it will move towards the positively charged electrode or towards the anode. Therefore, at pH which is equals to your 7.4, at that particular pH, your amino acid would be negatively charged and it would move towards the anode. The next question says the titration curve for arginine is shown below. Which of the following ionic structures would you expect at pH 8? So see, at pH 8 the overall charge of the amino acid would be plus 1, and as your pK1 is 2.1, so once the pH crosses this 2.1 value and until it reaches 9, the ionic form would be plus 1, and that is till below 9 it would be in the plus 1 state. So if you see that for A the charge is 0, for B the charge is plus 2, for C the charge is minus 1, and for D the charge is plus 1. So the right answer would be your D. Question number 5 says the two amino acids having R group with a negative net charge at pH 7. So the pKa of the R group of aspartic acid and glutamic acid are minus 3.65 and minus 4.25 respectively. Therefore, you would be seeing that at a pH of 7, the forms would be aspartate and glutamate, and it would be having a overall negative charge. So therefore, the right answer is C, where we would be having aspartic acid and glutamic acid. Now, which of the following statement is correct? Leucine is commonly used as an ingredient in buffers of SDS page. Tryptophan and tyrosine are more polar than phenylalanine. Aspartate is beta-branched amino acid, and lysine is a basic amino acid with the imidazole group as the side chain. So here the correct answer is B, because tryptophan and tyrosine contains indole ring for tryptophan and there is a phenol group for the tyrosine, and the side in the side chains, and therefore whereas if you see that phenylalanine has a benzene ring, so tryptophan and tyrosine will be more polar than your phenylalanine. So right answer is B. Now the Henderson-Hasselbalch equation does not explain the behavior of di and tribasic weak acids. It is usually useful with solution of acetic acid and hydrochloric acid. Now relates the pH of a solution to the pK and the concentration of acid and conjugate base, or allows the graphic determination of the molecular weight of an weak acid from its pH alone. So when you go into the Henderson-Hasselbalch equation, pH equals to pK plus log conjugate base by acid, and it definitely relates your pH to the solution of the pKa. So the whereas it does not explain any behavior of your dry and tribasic acid. So about the basicity and acidity does not speak of anything, and it is also not useful with no information about such usefulness about the solution of acetic acid and hydrochloric acid is given, and also it is for a buffer solution, and hydrochloric acid is a strong acid. And the graphical determination of the molecular weight of a weak acid also cannot be done from the pH alone. So the right answer is only C, that is 3 only, that it relates the pH of the solution to the pKa. Now, among which of the following amino acids has the highest molar extinction coefficient? So if you see that there are three aromatic containing side chain amino acids like tryptophan, phenylalanine, and your tyrosine. So tryptophan has the highest molar extinction coefficient, and it shows a highest absorbance also at 280 nanometers. So A is the right option. Now, which of the following is correct about the absorption spectra of amino acids? So you would be seeing that due to increase in polarity, conjugation is reduced, and consequently the energy gap is increased, which results in the blue shift, and the band position moves towards a shorter wavelength. So the right answer is B, where we are seeing an hypsochromic shift which occurs when the polarity increases. So blue shift is the hypsochromic shift, and when on increasing the polarity the band moves to a shorter wavelength, or the hypsochromic shift is seen to occur. Now, which among the following has or have the most chiral centers? Isoleucine, serine, tryptophan, and threonine. So in terms of the chirality, when you glance through the amino acid structures, you can see that isoleucine has two chiral centers, and your threonine also has two chiral centers. So among these amino acids, isoleucine and threonine is going to have. So 1 and 4, that is option D. Okay, moving on to the next question. Identify the amino acid with the lowest value for hydropathic index. So if you see that the lowest hydropathy index means highest hydrophilic nature, and highest hydropathic index means more hydrophobic in nature. So among histidine, lysine, arginine, and asparagine, you would be seeing that arginine has the lowest hydropathy index, that is, as it has the most hydrophilic side chain. So arginine is the right answer, and option D. Sorry, so option C, which is arginine. So which statement about peptide bonds among the following is incorrect? It is stronger than an ordinary single bond, that is true. Has partial double bond character, that is also true. Is weaker than an ordinary single bond, that is incorrect. So only 3 would be incorrect. So I've discussed all of these in my slides, so you can go through them and you can get to the correct answer. So these are the questions which you would be only expecting in your exams and assignments. Now a peptide has 85 amino acid residues with a molar extinction coefficient which is given, and a molecular weight of 10.2 kilodaltons. If the peptide contains 4 tyrosine, the absorbance value of 0.39, then calculate the number of tryptophan and the concentration of the protein solution. The extinction coefficient values for tyrosine and tryptophan is 1280 and 5690 respectively. So the epsilon value for a peptide is given to be 39 260. So you know this, and you know the molecular weight as well. And also it is that you know that only the aromatic side chains contribute to the molar extinction coefficient, and molar extinction coefficient is an additive quantity, so you can add them. So when, and also you know the extinction coefficient of tyrosine and tryptophan. Okay, so this is given. So now when you calculate 4 into tyrosine, which is given as the molar extinction coefficient of tyrosine, 4 into 1280 plus x into 5690 equals to your 39260. Then you can calculate it x, and it comes to be 6. So there are 6 tryptophan residues. Now when you know the molar extinction coefficient and the absorbance is also known, so you can calculate the concentration. So the epsilon value is given of 39260, and you know the absorbance to be 0.393, and you know the length to be 1 centimeter. So the concentration is equals to, when you calculate it, it's coming around 0.01 millimolar, or 1 into 10 to the power minus 5 molar. So therefore option A is the right answer. This value you are getting in what manner? I am repeating this question. So 4 into, because 4 tyrosines are there, and how many tryptophans we do not know. So 4 tyrosines, and the tryptophan is number we do not know, that we have to calculate. So we do it into 4 into 4, and this is x. Okay, so in this manner we can add them. So 1280 into 4 and 5690x equals to 39260, and there you calculate the x, it comes to be around 6, and you know the absorbance divided by molar extinction coefficient and your length, which is 1 centimeter, will give you your concentration, and that's why it's 6 and 0.01 millimolar. The correct 1-letter code for the tripeptide asparagine, tyrosine and lysine is, so asparagine is your N, your tyrosine is Y, and your lysine is K. So the right answer is A. Now which among the following combinations of torsional angles is correct? So when you see that, so I am mentioning here the torsional angles. The correct answer over here is C, and so the torsional angles which are involved over here is this one, and this one. So the first one is your psi between C and C alpha. So between C and C alpha is your psi, between C alpha and N is your phi, and between N peptide bond is your omega. So remember these 3 things, that will be only enough. So that's all for today. Sorry, there was a technical glitch, can't help out that, and this video is being recorded, so you can look into the YouTube video, as well as I would be sharing my slides, so you can take them as references for your help. Okay, so that's all for today. Thank you all for joining the class and attending the live session. Meet you in the next week. Thank you.